Hello everyone and welcome back to the show. It's your host, Eno Canny, here. The weather is getting a little chilly, isn't it? Today is October 13th, or Monday. Let's warm up our minds with a super interesting paper from the archives. Okay, let's get right to it. Today's paper is titled, Mode Learning Compositional Representations of Complex Systems with Mixtures of Dynamical Experts. Phew, that's a mouthful, isn't it? The curl is also quite long. Bertsiv. Bergsivage at 10.9594 von. It's from the category which, as you all know, stands for machine learning. So what is this paper all about? Well, imagine you're watching a group of tiny cells. It's like looking at a super busy schoolyard from above. Some cells are just running around in circles playing a game. This is called the cell cycle. But then some cells suddenly decide to leave the game, and they run off to become a different type of cell, like a skin cell or a muscle cell. This is called branching. The tricky part is that this change can happen in a very crowded, messy area. It's hard to tell which cells are going to keep playing, and which ones are about to leave. Older AI models had a really tough time with this. They would look at this messy spot where cells are going in different directions, and they would get confused. They would try to find one single rule to explain everything, so they would just average it all out. It's like if some kids are running left and some are running right. The old AI would predict that everyone is just going to run straight down the middle. But that's not what's happening at all. No one is actually going down the middle. This is a big problem for understanding what's really going on. This is where today's paper, Mode, comes to the rescue. Mode stands for Mixture of Dynamical Experts. Let's break that down, shall we? Mixture means it's a mix of things. Dino means it's about stuff that moves and changes. And experts, well, that's the super cool part. Instead of having one rule for everything, Mode uses a team of little experts. Each expert has its own special rule. An expert might be really good at understanding the cells that are just cycling and playing. Another expert might be a specialist in understanding the cells that are branching off to the left. And a third expert knows all about the cells branching to the right. And how does Mode know which expert to listen to? It has something called a neural gating mechanism. Let's just call it the traffic cop. This traffic cop is super smart. It looks at a cell and where it is, and it decides which expert's rule to use for that specific cell at that moment. So when a cell reaches that messy fork in the road, the traffic cop points and says, okay, you listen to the meta-known expert. Our rule should follow the branching expert's route. This way, it doesn't get confused and average everything out. It can make sharp, clear predictions about where each cell is going. Isn't that clever? So how can we use this in our daily lives? Let me give you a few examples. First, let's talk about medicine, which is what this paper focuses on. Imagine a doctor is looking at data from a patient's cells. Some of these cells might be healthy and just dividing normally. But some might be starting to change and become dangerous cancer cells. They are branching off from the normal path. Mode can look at all this data, and all by itself, figure out which cells are behaving normally and which ones are changing. It can even predict when a cell is about to make that dangerous decision to change. The paper showed it could predict this about a quarter of a cell in advance. That's an amazing early warning system for doctors. Second, let's think about self-driving cars. Right? A car driving down a road is a dynamical system. Usually driving is smooth, or what happens at a busy intersection. A car might need to suddenly brake, or quickly merge, or wait for a pedestrian. These are different dynamic regimes. A single AI model might get hesitant, trying to average all the possibilities. But a car with Mode could have an expert for driving, an expert for emergency braking, and an expert for merging. The traffic cop inside the car's brain would switch to the right expert instantly, making the car's actions much safer and more decisive. And for a third example, how about predicting the stock market? The market doesn't just go up in one smooth line. Sometimes it's in a bull market, where things are growing. Sometimes it's in a bear market, where things are going down, and sometimes it's just stable. These are different behaviors or regimes. Mode could learn an expert for each of these market conditions. By figuring out which expert is in charge right now, it could make much smarter predictions about what will happen next. So compared to other technologies, like the ordinary differential equations or nodes that the paper mentions. Mode is much better at handling these sudden changes in branches. Nodes are great when things are smooth and predictable, like drawing one long continuous line. But when you hit a fork in the road, you just draw a blurry line down the middle. Mode is like having a whole box of colored pencils. You can draw the main path in blue, and switch to a red pencil for the left branch, and a green pencil for the right branch. The final picture is much clearer and more accurate. So to wrap it all up, mode is a wonderful idea that helps us understand complicated things by breaking them down into simpler parts. It teaches us that sometimes a team of specialists is way better than one person who tries to know everything. That's all for today, everyone. I hope you had fun learning with me. Stay curious, and I'll see you next time. Bye-bye.